Hi class, welcome to the second half of lecture for today. So what we're going to talk about in this segment is this question of what we mean by habitability. So we're talking about exoplanets, and we're talking about how to find exoplanets in the universe. That in and of itself is certainly an interesting question, but since we're ultimately interested in life, we are interested in some of the exoplanets more than others of them. Okay, and this all centers around this question of what do we mean when we say the word habitability. Okay, so we're going to talk about the definition of that today. We're going to talk about what influences that when we talk about individual planets, and then we'll use that to motivate our discussion for examples of habitability that we've seen and how we're going to actually look for it in other planetary systems around the galaxy. So in the background today, this is an artist's rendition of an exoplanet system as viewed from its moon. One of the great things about art is we can imagine things that we can't see in our telescopes, what they might look like if we were actually there. We can imagine things and represent things that we're actually looking for. And what I like about this image in particular is it highlights something we're going to talk about, which is the conditions that you experience on a world. So the conditions on the surface of this moon here versus the conditions that you see on the parent planet there in the background are substantially different, even though they both are roughly the same distance from the parent star, which you can see in the background. So you'll remember in the first half of lecture, we talked about how the properties of the parent star influence the amount of energy that you receive at the location of a planet. Well, a moon and a planet are going to receive more or less the same energy from the parent star. But what you can see, if you look at that planet, it looks like it's definitely Earth-like and has Earth-like conditions on it. Okay, the conditions on the planet are substantially different than the frozen conditions that you see here on this moon. Okay, and that has to do with the properties of the planet itself. And so that's what we're going to talk about in this segment. Okay, so let me go ahead and start some slides. I don't see them in my, let me try that again. Who knows what Zoom is doing, right? It's always something with Zoom. Oh, there they are. Okay. Okay. So if you talk to astrobiologists or exoplanet people, what we're talking about is generally goes by the name the habitable zone. You will sometimes hear it talked about, particularly in popular science literature, as the Goldilocks zone, referencing the Goldilocks and the Three Bears, where is it just right for plants to have life. I prefer the word habitable zone to Goldilocks zone because it's a little more clear what we're talking about, although as we'll discuss here, the word habitable itself is a little bit ambiguous as well, okay? So we'll start right there with that point exactly. We'll define habitable. We'll talk about how the properties of the planets affect what we're calling habitability, and then we'll combine that with the influence of the parent star to talk about what we mean by habitable zone in our discussion. Okay, so when we say the word habitable, what we usually mean is hospitable to life. Okay, and that is, as we've discussed many times during this quarter, very loaded because it inherently incorporates our biases as to what life means, what is life, and in particular, what life needs to thrive. And as we've discussed many times, we really only know about life on Earth. So when we say someplace that's hospitable to life, what we're really saying is a world that would be hospitable to life that's similar to what we see on Earth. So really, when we say the word habitable, what we mean is for a world that's similar to Earth, where could you be such that liquid water could exist on the surface? And that statement sounds weird because you're talking about water, which is only one of the conditions of life. that we said we're going to look for. But there's a whole bunch of physics hiding in that statement because we said liquid water and on the surface. And those imply certain conditions and certain chemistry that's going on that's implied in that statement. And so whenever you hear the word habitable, you really should think about this statement here. This is what astronomers are really trying to say. We're looking for an Earth-like world. Could it have liquid water on the surface? Okay, now that is not a simple yes or no answer. If I just hand you a world, you cannot look at it and say, yes, it's in the habitable zone, or no, it's not habitable. Okay, that is because habitability, the conditions under which that statement are true, is enormously complex, right? There's a whole bunch of physics and science that goes underneath that because it depends on the properties of the star, it depends on the properties of the planet itself, and it depends on where the planet is with respect to the star. Okay, and you have to fold all of those things together. And so this question of habitability feels like a lot about this kind of wishy-washy back and forth. And indeed it is, because as we'll see on Friday when we talk about this with regard to habitability in our own solar system, the rules aren't hard and fast. The conditions exactly on the planet, the conditions exactly how it's evolved and how it's experienced its history with this star can push a planet to be habitable or not habitable, even though it may indeed be in this so-called habitable zone. Okay, so this is really, it's like pirate astronomy, right? This is really a set of guidelines rather than a set of rules. Okay? Okay, so let's talk about the conditions for liquid water, because that's really at the heart of this. Okay, so the first condition for liquid water is there has to be enough pressure on the surface of the planet to keep it from evaporating. Now, we've kind of obliquely talked about that because there's no liquid water on the surface of Mars right now. That's because the surface pressure on Mars is so low that the water has all evaporated away, and its gravity is so low it's escaped to space. Okay, so it's really, this is kind of a statement about surface gravity, and we'll get back to that. We'll talk about surface gravity in just a minute, because the surface gravity of the planet has to hold on to the atmosphere. But the surface gravity combined with the properties of the atmosphere affect the pressure on the surface of the world. But generically, the surface gravity means that deeper atmospheres have higher pressure at the bottom if the surface gravity is the only thing responsible for pressure. Now, you've all experienced that before in a swimming pool. Okay, so you know that if you're floating high up in the water in the swimming pool, the pressure on your ears isn't very bad at all. But if you swim down to the bottom of the swimming pool, then the pressure is really enormous and it can really hurt your ears. And the reason for that is because of the surface gravity of the Earth. If you're floating there in the middle, then the pressure that you feel in your ears is caused by the weight of the water that's over your head, which isn't very much water at all. It's not very deep water. Okay, but if you're on the bottom of the pool, the pressure that you're feeling in your ears is the weight of all of that water above your head pressing down on you because it's deep. Atmospheres are just like water. They're fluid. And so the deeper you are in the atmosphere, the higher the pressure. And that influences whether or not you can have liquid water on the surface. Okay, but how strong that pressure is strongly a function of the surface gravity of the planet. Okay, so I'll remind you that you can compute what the surface gravity of a planet is. Okay, it's the Newton's constant G times the mass of the planet divided by the radius of the planet squared. Okay, so we've calculated that before. So if I wanted to calculate the surface gravity of Mars, okay, the surface gravity of Mars is only about 3.72 meters per second per second. It's about 40% the surface gravity of Earth. Okay, so Mars has a very thin atmosphere. The pressure on the surface is low. That's because the surface gravity is low. And it's because over time, Mars's surface gravity hasn't been enough to retain the atmosphere on the planet. It's escaped to space, as we've discussed before. Okay, so clearly Mars gravity isn't enough to guarantee that a planet's surface is going to be habitable. Okay. By contrast, if I were to calculate the surface gravity for Earth, then I get 9.80 meters per second, and clearly that is a strong enough gravity to retain the atmosphere of Earth, and the surface pressure on the Earth is certainly allows liquid water, because we see plenty of liquid water all over the surface. Okay, so this is one part of computing whether or not a planet is capable of supporting liquid water on the surface. What's its surface gravity? Is it strong enough to retain an atmosphere? And if there is an atmosphere, is it strong enough to help the pressure at the surface? There are other things that influence the pressure as well, which we'll ultimately come back to. Okay? Now, the other issue with liquid water is that the temperature has to be high enough for it to not freeze. Okay? So that is an influence of the star on the planet. So the star is outputting some amount of energy, okay? And depending on how far away the planet is, it receives all of that energy, okay? It absorbs it, but then it re-radiates it out to space. And the temperature that you have on the surface of a planet is the balance of those two effects. How much energy is incoming versus how much energy am I shedding? Okay. Now, the surface of the moon, as we discussed with the picture behind us at the beginning, can be quite different than temperature than we have on the surface of the Earth. And the reason for that is the Earth isn't a bare surface the way the moon is. The Earth actually has an atmosphere, and the atmosphere acts like a blanket. So all of the energy that comes in and hits the Earth, it tries to radiate away, but not all of it can get away. Some of it is retained by the atmosphere underneath it, just like a blanket keeps you warm. And so the atmosphere insulates the planet, it retains heat, and so the surface temperature of the Earth is warmer than the temperature it would be if it was completely exposed to outer space. Okay? So the properties of the planet, in particular its atmosphere, are crucial to whether or not it can be habitable by that definition. Can the planet have liquid water on the surface? You could take the planet Mercury and put it in the Earth's orbit, and it would not be habitable because it doesn't have an atmosphere. Okay, liquid water couldn't survive on the surface of Mercury, whether it was in the Earth's orbit or not. Okay, so the conditions, the properties of the planet affect the conditions of that definition dramatically. Okay, so let's look at the sun's habitable zone. So this is a figure from your book. There are two different ranges, what they call the conservative range and what they call the optimistic range. Okay, so I marked here the optimistic range. I think they are the appropriate ranges to consider because the conservative range really is very aggressive about whether or not the conditions on Earth are unique or not. The conditions on Earth and Venus, as we'll discuss next class period, the planets are very similar in size and composition, and so you can imagine they were very similar in terms of their early history, but Venus is very different than the Earth, and the reasons for that are complex, and those kinds of discussions are the things that influence our discussion of whether or not we think the habitable zone is conservatively small or optimistically larger. But let's take for the moment it's optimistically larger. So from the perspective of the parent star, what matters is how much energy you're getting from the star. And we call that the stellar constant. Okay, if you're talking about the sun, it's usually called the solar constant. So if you go look it up on Wikipedia, it'll be called the solar constant. We usually call it little k, and it depends on these properties that I've written here in this equation. So L star is called the luminosity. It's basically the brightness of the parent star. It's how much energy is the parent star giving off, which is a function of its temperature and a function of its size. And there are physics ways for computing what the size of that number is. You can just look them up for most stars. If you go to the Wikipedia page for Vega, it's going to tell you what the luminosity of Vega is, okay? In the denominator there's 4 pi, that's just a constant, but the d is the distance between the star and the planet. So you see it's there d squared. This is the 1 over r squared, or the inverse distance squared law coming in here, okay? So the amount of energy, k star, per unit area that you receive at your planet depends on 1 over the distance squared to the planet, okay? So if I were to put in the properties of the sun here, okay, so I put in the luminosity for the sun, I can look that number up, and then I put in the value for the inner conservative, for the optimistic inner radius of the habitable zone, and also put in the outer radius for the optimistic habitable zone, I can compute how much energy is required on the Earth to keep water from evaporating, that's at the inner zone, or keep water from freezing at the outer zone, okay? So the inner zone, okay, if the Earth were to get any closer than that inner zone line, the amount of energy we get from the sun would be so much that it would be too hot on Earth for liquid water to exist on the surface. Okay, so if the energy input from the sun exceeds 1,925 watts per meter squared, which happens at about 0.84 AAUs, okay, 0.84 the Earth's current distance from the sun, then we wouldn't be able to have liquid water on the surface, okay? Today, we get about 1,360 watts per meter squared at a distance of 1 AU, and clearly we can have water on the surface, okay? But if we went out past Mars's orbit, okay, to 1.7 times the current Earth orbit size, then the energy drops to 470 watts per meter squared. And at that point, water would freeze on the Earth. Earth would turn into an ice ball, like planet Hoth, okay? So that defines the ranges in our solar system where if you put the Earth down, you can have liquid water. And so we're going to use those same numbers to talk about other stars. Those K star values are the values that we care about. And if we use them together with the properties of the star, we can calculate how far away from the star you have to be in order to have liquid water on the surface of a planet, okay? Now, I will point out for most of you, you may occasionally read, let's call them improper things on the internet, okay? So we all get all kinds of crap spooling through our social media. And in particular, wrong astronomy facts come up all the time, okay? So in particular, one of the things that you will often see is a completely false statement that if the Earth were 1 mile closer to the sun or 1 mile farther away from the sun, we wouldn't enjoy the nice climate that we have here on Earth. Okay, well, as you can see from this calculation, the habitable zone is far wider than just 2 miles wide. Okay, so we can exist over a wide range of distances from the sun, and the Earth would still be habitable. Okay, that statement, by the way, if it ever runs across your feed, you know it's false anyways, because the Earth's orbit changes in distance to the sun by much more than 2 miles over the course of a year, and the Earth doesn't suddenly freeze over and thaw off during the year, right? Right. Okay. Well, us in Chicago and polar vortexing may differ, but that's another story for another day. Okay, so how can we use this to talk about stars? So I'll say to most of you that this equation here, this is the level of math that we said at the beginning of the term that we would have to be capable of doing. But I'm putting it here for reference. We're going to use it. I want you to know how we determine the things we determine about planets. And I'm not expecting us to actually do any calculations with this, although you are certainly welcome to, and you may want to go off and think around on with it for yourself. Okay, but let's talk about how we would use this for finding the habitable zone around another planet. Okay, so I can take this equation and do a little bit of algebra, and I can solve for the distance instead. Okay, so if that amount of algebra there causes you some anxiety, you and I should talk, because I certainly think when you leave your college education, this amount of algebra should not cause you anxiety. But it's a couple of steps, and you should be able to do that. Okay, so what I've done is I've taken that one equation, it's still the same equation, and I've just written it down in terms of the distance. And so if I look up the value for the star's luminosity, and if I know the value of K star I care about, which the values of K star are basically where does water evaporate, where does water freeze, okay, then I can compute the size of the habitable zone around any star for which I know the value of L star, okay. Well, as it turns out, if you're on the main sequence, the values of L star are well established for you. Okay, every star on the main sequence has a given spectral class, and for those spectral classes, there is a well-defined value of L star, which I've put in this table here. Okay, now I've done this for a few of the different classes. You'll remember I said there are 10 different spectral classes inside, so I've just done it for 0 and 5 for each of the spectral classes. For those of you who want all the numbers, I have this all in a spreadsheet. I can send it to you, and you can play around with this to your heart's content while you're watching Netflix. Okay, but you can see as you go from the hot big stars. Okay, so those are the O-type stars in the main sequence. Those have very large luminosities. They're very bright. They're putting out huge amounts of energy. Okay, 1.91 times 10 to the 32. Okay, if I go all the way down to the other end of the main sequence, okay, the M dwarfs, they are putting out, it looks like 100 million times less energy. 2.91 times 10 to the 24, 100 million times less energy than their O-type companions all the way on the other end of the main sequence. So there's a wide variety in the amount of energy that stars output. We can compute where the habitable zone is from those numbers, okay, using our D formula over there on the right, okay? So what does it end up showing us? Well, that's very easily shown in a heuristic picture. There's a picture of this in your book. I don't like the picture as much as I like this one from NASA, so I'll show you this one. So there's basically 3 stars shown here in this figure. There's a sun-like star in the middle. There's a much hotter star than the sun, so say Sirius or Vega or Spica. And there are much cooler stars than the sun, Proxima Centauri, Wolf 359, stars like that. And so what you can see is if you know where the habitable zone is for the sun, that greenish region there, okay, then for a star that's cooler than the sun, the habitable zone is much closer to the parent star. And for a star that is much hotter than the sun, the habitable zone is much, much farther away from the parent star. Okay, the red zones here are regions where water would evaporate on the surface, where a plant would basically be baked by the star, and then the blue zones are regions where the planet would ultimately freeze. I will say this is related to where the icy worlds are in the solar system as well. If you go far enough out, you reach a distance from the star called the frost line. So if you go reading about this, you'll sometimes hear the frost line or the snow line talked about, and that's the region where all the icy bodies formed in the early solar system. That also is a function of how much energy is given off by the star. Okay, so the reason we care about this is because we're going to start looking for exoplanets around other stars, and we're going to find them at all different distances from the stars. But if we want to talk about the ones where we have a hope that life might exist, then we really care about the ones where the habitable zones are, which is why we need to know how far away from the star should we be looking for planets to find planets in the habitable zone. Okay? Okay. So that's all I'm going to say for lecture today. So this is kind of mixed in your book between chapters 10 and 11. So I'm kind of consolidating the information to tell the story that I want to tell you. So if you're trying to read about this in your book, it's kind of spread between chapters 10 and 11. If you read the 2 chapters together, you'll get everything. Okay? So that's all for today. I hope you're all doing well. Stay safe, and I will talk to you next time. Take care, everybody.